Okay. So we're going to talk about this very central problem in graph algorithms called sparsest cut. Actually, today's going to be about a technique for it called L1 metric embeddings. Okay. Uh, One of its famous applications is to the sparsest cut problem. But given that the class is chopped in half, in the old version, I used to like introduce sparsest cut, get that motivated, and then do the L1 metric embedding. I'm going to flip it. We're going to try to do the L1 metric embedding, get that done as a tool, and then next class we'll worry about the sparsest cut problem and use it. So the reason why this section is going to be offered now. So last week, we're doing this high dimensional stuff, right? This idea of dimensionality reduction, where I just project down using Gaussian random variables, and sort of as an extension or similar ideas, um, was again doing some kind of projection here to do some kind of hashing scheme for faster lookups, right? So what we're doing today is also, in some sense, some kind of metric-based thing, but it's a little more combinatorial in nature. So in a full class, we would do all these at once, but since our class is a little shorter, so today we'll just try to focus on the embedding part of it, which is really the randomized part of it. And we'll talk about these L1 metric embeddings, and then we'll deal with graphs next time. If I have time, I can still introduce it a little bit today. So, okay, right. So last time, or last week, we looked at this kind of thing. And so one thing to note is that we're working from Euclidean space and going into Euclidean space, right? I'm looking at distance in terms of sum of squares in one, and I'm looking at distance in terms of sum of squares into the other. But this could be generalized, right? This could be any metric going to any metric. And hopefully this metric is somehow smaller or more convenient or has nice structure, things like this. Okay, so today we're going to have just a generic metric here, just given as an oracle. Like, here's a function that gives you the distance between any 2 points. That can be applied to this, but it can be applied to anything. And then we're going to do what's called an L1 metric. So I'm assuming many of you have seen this before. So the L1 metric is the sum of absolute values of the coordinates. Okay. In some ways, it's a very natural metric. I don't know if this is very helpful, but if you want to plot out the unit circle in various metrics, L2 is going to be an actual circle like you expect. In L1, right, the distance is the sum of coordinates. So sometimes called the Manhattan distance. Okay, so it looks like a diamond. L infinity is looking at just the max coordinate. That doesn't come up today, but I wanted to draw a third picture. So it just looks like a square. So you have slightly different characteristics. L1 is arguably very natural for us, discrete combinatorial people, right? Like we're used to doing addition and subtraction and stuff. If you're doing continuous sciences, then L2 makes tons of sense, like, and it's focusing on the derivative. And we'll see next time when we talk about sparsest cut just how nice the L1 metric is. But this is the thing that resembles, for example, linear programs, right? So getting it down to L1 metrics is going to be useful. Again, I won't be able to really motivate this today. So here's the theorem we're going to try to show. So we're going to take as input any metric. Okay, so I'm just going to be, V is like a set of vertices or a set of points. It'll be a set of vertices in next time's application. And let's say there's n of them. So we're going to try to assign every point or vertex or whatever a point with like log square n coordinates. Okay, it'll be a random function, so f is generated randomly, and then it's a fixed thing thereafter. And the guarantee we're going to get is that for every pair of points, uv, so this is, I've embedded u, I've embedded V and I measure the L1 distance. So it's looking at the difference in coordinates. I'll add it up. It'll be at least the original distance and at most a log n factor bigger than this. Okay, so it's going to be, this is sometimes called log n distortion. So you're going to lose a log n factor in your approximation. There's many, this is in fact, but very good though. There's many problems for which this will give actually the best, say, approximation you can get. Again, we don't quite have context for this. But I know last week we got 1 plus or epsilon, so you're like, oh, why would I have log n? But you're getting log n in the L1 metric, and L1 metric is more convenient for some situations than log base 2. So sparse, yeah, there are plenty of problems where at some level it could be cast in a metric. Oh, here's your input and it's a metric, and it seems hard. But if your metric was an L1 metric, it's actually quite easy. The sparsest cut is just one of these that will come up next time, but there's a general paradigm of I'm solving some metric problem, and let me first embed it as an L1 metric. I lose a log n factor on whatever problem I'm interested in right away, and then I can solve the L1 metric exactly. And I just lose log n overall. Yeah. Yeah, you can project it again from this down to the next one. Uh, but your resulting thing down here, you're from now on going to work in the Euclidean metric. Okay. Actually, let me make 2 points clear. One is what we did last time was the Johnson-Lindenstrauss, the randomized embedding is preserving the L2 distance to L2. So it's not going to take L1 distance and turn it into L2. So first, just going from L1 and reinterpreting as L2, you're going to lose like square root n or something. So a bad example is like 1 over square root n everywhere. And then you're going to, then afterwards you only use 1 plus epsilon. That's, yeah. So, so we'll only touch on this in this class, but there's a whole field of like going from one metric to another in high dimensional geometry and things like this. This is partly just to expose you to some of this stuff. But it's a big topic in and of itself, this idea of metric embeddings. One thing, again, nice is that we can take any metric as input. This could be like the shortest path metric of a graph, for example. So you have an undirected graph, you compare all pairs shortest paths, you have all these messy things, you can embed in L1 and roughly estimate all the distances between vertices, right? So, yeah, anyway. So that's what we'll do. Any questions about the claim? Okay. So I guess here's the more formal version. I think the one I just showed you is this one as the corollary. The exact one we're going to show is slightly different. It's going to say, oh, if you use log n log 1 over delta coordinates, then you're going to have two properties. One is that this will be at most log of 1 over delta. You can think of 1 over delta as n. It'll always be at most log n times the distance. Okay? And then and it'll be smaller than the distance with probability at most delta, so it's 1 over n. So all I'm really saying is that one of these inequalities actually holds deterministically, always. And it's actually this one that we'll really focus on. Okay, but I guess the top form is what we'll directly prove, and then you just plug in delta is equal to 1 over n. So let's do that. Yeah. For any particular UV. And then if you set delta to be 1 over n squared, then you get the union bound. Yeah. Yeah. Won't worry too much probably about this today. I mean, at some level, yeah. The more interesting ideas are elsewhere. But I guess this is the way it's set up. Okay, so before I unveil this, I wanted to give you all an opportunity to think of ideas. Remember, this time you don't have it's just a generic metric. You can think of a shortest path metric as something to challenge your imagination, right? Because you don't have even have coordinates to work with. Any ideas for how to, yeah, like we can take that as a concrete example. So you've computed all pairs shortest paths. You know for every pair of vertices, the distance between them, it's an undirected graph. Okay. And now you need to assign to each vertex some set of coordinates, hoping that the L1 distance in this coordinate representation is somehow roughly reflecting the shortest path distance up to a log n factor. I'm just curious to see what you guys will come up with. Yeah, I wouldn't even worry about the dimension being log square n initially. Okay? I can give you the whole, I mean, I could even give you like a click where the length of the edge is the distance, right? So the adjacency matrix is the distance metric. Yo, yeah. Okay, I'm happy to hear. Oh, okay. But then how, yeah, but what's a reasonable, even just go from vertex to some kind of representation, right? Even, not worrying even about how many coordinates. I use an infinite number of coordinates. Just the idea of trying to take a vertex and code it. Okay, so maybe I can, F is going to map V to Rn, or RV, I guess. So the coordinates will be indexed by other vertices. Oh, we're doing the embedding. So each vertex is going to be given some kind of, coordinates. So, okay, so maybe you're saying, okay, Fu, uh, if you look at the vth coordinate, would be equal to distance UV or something. Of course, if we looked at, the difference between 2 points, that's going to be the differences of all the, it'll be something like this, right? Kind of thing. Oops, why did I put one there? Yeah, but at least it has the form of something we're looking for. Doesn't work. Well, to some extent, this is arguably not so far off than what would do. Okay, I don't know if this is guessable. So here's going to be the high level idea. So for some, this is to generate just one coordinate. Okay, and it's actually not so different than what was suggested, but a little more general. So we're going to sample every vertex in the graph with some fixed probability p. Like p is 0.1, so you sample like about a tenth of the vertices. And then for each like vertex v, you're going to make a coordinate, which is the distance from your set to v, which is to say, find the closest point in your sampled set. Uh, Yeah. So when I say like the distance from the set S to V, I mean, the minimum over all the points U in S, the distance from U to V. And that's one way to try to generate one coordinate. Okay. So yeah, what's some of the intuition behind this? Well, I guess you're hoping that, yeah, anyone want to suggest why at least this might be like correlated with something we're looking for? If you just enumerate all sets, it has to work out. That feels very bold. Uh, well, okay, here's maybe some intuition, right? You know, if let's say that W is very close to V, relatively speaking, and most points are far away, then if I look at these two distances, right, the distance from W and V from S are both somewhat similar by some kind of triangle inequality type of logic. So their L1 distance on that coordinate would be kind of small because they're both roughly the similar distance from S. So if neither of them gets sampled and they're much closer to each other than everyone else, then good. Now, if I did sample W or did sample V, so if W was kind of part of this set, well, you're still hoping that the distance from then W is going to be assigned value 0. So every value that's in S will be assigned value 0, and V will be assigned value from distance from V to the set, and W is maybe close to being the closest point in the set S anyway. So again, you'll get something that kind of looks like distance VW, right? So that at least, and I guess arguably that intuition could have applied to your previous suggestion as well. So you can think of maybe what we're going to do in the following as a more kind of calibrated thing. Um, yeah, so I don't know, some vague intuition for why this would at least be correlated with the distance between W and V. So yeah, so okay, so some level, yeah, okay. So the full algorithm is going to do this many times. So it's actually a very simple algorithm. Uh, so we're going to sample at different scales. So that we'll do a random set of size on average 1, and a random set of size on average 2, set of size 4, 8, 16, 32. So you do P for every probability of the form 2 to the minus I between 1 and log n, and that'll generate log n coordinates. And we'll analyze just one of these, and then you repeat those log n coordinates another log n times overall. But in one pass, you're going to sample each scale once. Okay, so the ith coordinate is going to be a distance from the ith sample to V. So that's the algorithm. It's somewhat simple. Oh, uh, okay. I think if SI is empty, you can just assign everyone gets the same value, so differences are 0. So we might as well assign them 0. It's still a contraction. Uh, yeah, I don't think it's too big a deal, one way or another. Okay, but the algorithm, that's the whole algorithm though. Right? So the question is, why does it work? Okay, so let's do that first. Let's say, okay, each of these coordinates I claim is a contraction. Okay, so I'm now going to use u sub I as the ith coordinate that's assigned to u instead of writing f of u I or something. Okay. So the claim is that every coordinate is a contraction. So why? Is it probably feels somewhat intuitive, but maybe we can just go through it. So here's like u, and maybe this is the closest point to u. This is like some t, right? So here's the full distance between them, right? And so the claim is that the difference between these two is always at most the difference at most this. The difference between the two smaller ones in the picture is always that long hypotenuse. Okay, that seems pretty obvious in the picture. So maybe I don't know what the bad example would be. Um, oh, here's one thing. So ui minus vi, which in this picture would be dut minus dvs. So t refers to really the minimum point. S refers to the minimum point. Okay. This should be at most dut minus dvt, right? Because S is the closest. Or did I get that backwards? I got it backwards. Right? And now what? Okay, so this thing is at most duv plus dvs. Then the minus dvs will cancel it out. So that's one direction of the absolute value. The other one will be the same. Okay. There's probably a nicer proof by picture, but oh well. Okay. Okay, so that's the contraction. So if you kind of do this, if the set S was a single point, this claim is pretty clear. That's immediate triangle inequality. When you do this minimum, you just need have one step of indirection in between. All right, so every coordinate is a contraction when we do these Frechet embeddings. Frechet is a person for context from a long time ago, and so the more interesting part is trying to show an expectation will get at least a constant fraction of the distance with all the coordinates added up. So before it was a coordinate-wise contraction, which means that it's going to expand by at most log n times because there's log n coordinates. And now we want to show that it expands at least, say, distance uv divided by 100 or something on average. Okay, so this is the more subtle part. Okay, so the setup somehow is very subtle. So for ease of notation, I'll let delta denote the distance between them. And then here's the kind of clever thing. For every index I, say from 1 to log n, we're going to try to choose Ri to be the smallest radius so that if I drew the distance Ri ball around each one, each has at least 2 to the I vertices. Okay, so somehow you're going to focus on these radii that's adaptively chosen to make sure that you have enough vertices in each ball. Somehow this is very important. And the claim is that, the immediate claim, is that for each of these indices I between 1 and log n, with constant probability, the I plus 1th coordinate is going to contribute at least. So the interesting case is when Ri is smaller than delta over 2, otherwise the balls are crossing. So only when Ri In one case, when Ri gets very big, we'll handle that. In a more interesting case, Ri is smaller than delta over 2, in which case the I plus 1th coordinate is going to give you at least Ri minus 1, where Ri is this radius to barely contain 2 to the I vertices. Um, Maybe it would be helpful to see why this claim would finish the proof, so I can leap ahead to motivate the claim. So if this claim were true, then how could we, just to make sure we were kind of on the same page about RIs and deltas and stuff, if this claim was true, how would I prove the overall lemma? Well, I'm not sure if telescoping is the right word, but so what are we interested in, right? We're interested in this thing, right? So we can sum up all these coordinates. Uh, Something like this. Okay. And then this is going to give us a bunch of, I guess there'll be some biggest k. If k is like the last index that's smaller than delta over 2. So you're going to get, okay, let me do this more slowly. Sum over I, the expected value of the coordinate. So here this is just linearity of expectation. So to say that this thing is at least this thing a constant fraction of time is the same as saying, or implies, the expectation of this thing is at least a constant times this thing. Okay, so let me write it out slowly. Some constant c, uh, min ri delta over 2 minus min ri minus 1 delta over 2. Okay. And so only like there's going to be one term of the form delta over 2 minus ri for some large I. And then the rest will be ri minus 1, ri minus 1. So they'll all telescope out. And I guess r0 will be 0 because radius 0 is 1 point in the ball. So, yeah. This part here? No, this is just, so let's say that the constant probability is 50%. Okay. So 50% of the time, this is bigger than this. So if I want to know what the expectation is, the average, it's at least 50, half of this. That's all, yeah. Um, so this will telescope and you'll get delta over 2. I guess there's some constant c. Yeah. Yeah, so what's the worst case if the good thing doesn't happen? Yeah. So luckily, because the absolute value makes it non-negative, so we can just ignore the uh yeah. So if I just do this, uh so if you get 100% on the midterm half the time, you'll get at least a 50% on average. You might do better if the other times you do even better, but you're just overthinking it. Yeah. So the point is that this is setting up some kind of telescoping series. So if we could just focus on one scale roughly getting Ri minus 1, that's the interesting one, then we're in good shape. Okay, and then everything will follow. So let's do that. Okay, for each index I, the claim is that, okay, this ith coordinate is going to contribute, I plus 1th coordinate is going to contribute a lot. So let's see. Okay, so let me focus on the case where Ri is at most delta over 2. So in that case, it does kind of look like this, where the Ri should not touch, the balls don't touch, because they're far enough apart. Okay? Now, okay. So I'm going to assume that, okay, so Ri is determined either by U or V, right? Ri is just small as possible until, so let's say it's determined by U. So that means if I kind of look strictly inside, uh, strictly, there's at most 2 to the I in U. So the 2 to the ith will have to be on the boundary. Okay. And um, right. Now, if I look at a slightly smaller ball, uh, here, oh, that wasn't supposed to happen. Okay, and this one was r to the I minus 1. Then inside here, there's at least 2 to the I points. Okay, because that's how 2 to the I minus 1 points. Okay. Now, okay. So, okay. Suppose I sample a point inside here and I don't sample any points on the left. Okay. Suppose I sample a point in the smaller one, but I don't sample any points in the bigger one. Yeah, so let's say this, we're looking at the SI plus 1th sample, but I'm focusing on the balls of radius I and R and radius Ri minus 1. Okay. So if I sample a point here but not there, then what's a lower bound on Ui plus 1 minus Vi plus 1? And why? I don't know why I drew it so small. I'll zoom it out while you guys think about it. Yeah. Yeah, so what you're interested in ultimately, right, is d u si plus 1 minus dv si plus 1. So you want this to be something comparable, right? The claim is that this is going to be at least ri minus 1 sometimes. So for that sometimes, suppose that I plus 1 sample managed to avoid these at most 2 3i points, and but did sample one of these 2 3i minus 1 points, or at least 2 3i minus 1. Then what? Okay, so let's just look at each of these terms. What do I know about this in this scenario? It's at least Ri because I know it's not in this ball. There's no points in the ball. And then what about V? It's going to be at most Ri minus 1, and there's a negative sign, so you still get the greater than equal. At most Ri minus 1 because it's inside this ball. So if I can hit this and not hit that, then I'll get that term I'm looking for. Right, so that's good. So now what's left is what are the odds of that happening? So Si plus 1 is going to, this is where P is equal to 1 over 2 to the I plus 1. Yeah, so we expect to sample, like an expectation, how many do we expect to sample from this set? Every point of sample is probability 1 over 2 to the I plus 1, like half, right? So we're hoping, oh, you probably don't hit this. And now you want to say, oh, do I at least hit this? Well, what's the expectation here? At least a fourth. Now, one thing really critical, so you would have to be kind of lucky here and kind of lucky here, right? We'll do it more exactly in a moment, but you might say, oh, there's a constant chance of getting less than 1. That's from Markov's. And then maybe we can show there's a constant chance, right, of getting 1 here. And now one thing really nice is what these points, because they're separated, are completely independent from these points, right? So there's some constant chance of good, constant chance of good, and then you multiply the two together and you get constant chance of good, good, right? So, um, so we can do the calculation. I think it's not too, uh, yeah. Sampling from inside of, uh, we need both of these. So making sure you don't hit the U ball guarantees that the coordinate is at least Ri. Oh, yeah, we're trying to prove that this happens constant fraction of the time. So ignore delta. I'm in the regime where Ri is smaller, and I'm just trying to prove something relative to R over 2. Ri over 2. Ri and Ri minus 1, sorry. And then remember that at the end, all the Ri's will add up, and it's okay. Um, yeah. Okay, so constant chance, constant chance. This one you would do 1 minus p to the 2 to the I minus 1, and you get like e to the minus p over 2 to the I plus, or you get e to the minus 2 to the I minus 1 divided by 2 to the I plus 1. So you get like e to the minus 1/4 or something. And here just by Markov, there's a 1/2 chance that this is good. Okay, so that's nice, that's cute. Um, the other case is where Ri is greater than equal to delta over 2. Maybe I can just duplicate this. Okay, so the other case is where this becomes a greater than equal to. Okay, but that means this is bigger than Ri minus 1. Okay, so the picture will change a little bit because, let me do this one. This radius should really look like halfway through the line or something. Does that look like it's halfway? Oh, maybe I should make this bigger. Something like this. Okay, so can't quite go Ri, but delta over 2, but then you'll get the same observations. It'll be okay. Let me just double check. Yeah, okay, it's the same. Okay, so because we truncate at delta over 2, so that still guarantees the two balls are disjoint. Delta is half. Ri minus 1 is smaller than delta over 2, and you'll get the same argument. Yeah, it could be much bigger. So this is no longer radius Ri. This is now radius delta over 2. Yeah, yeah. But the U is still the one that determined the Ri. But the real thing is the disjointness. Making the ball smaller is only going to help you with this less than 2 to the I strictly inside. And that's what we need. Yeah. Yeah. Yeah, and the probability of each point was independent was 2 to the I plus 1. Yeah. Okay. So good. So I think that proves the claim, and that tells us an expectation. One of these log n rounds where I do one set S at each scale is going to get me the right distance and expectation. Okay. Now the overall claim, now all that's left is kind of okay. So that gives you this, with log n dimensions, you can guarantee that you expand at most log n because each coordinate is a contraction. And an expectation, you'll get, 1/10 of the distance. So the log square n dimension one was a little bit, well, bolder. It says that, okay, if I choose log square n, if I do something for log square n dimensions instead of log n, then I can guarantee that with high probability, uh, I'll get a most log n and I'll expand everyone. So right now, an expectation, a single pair is good. And now I want to show that with high probability, every pair is good. So what should I do? Okay, I think you're saying we should do it log n times. Okay. So now I have log n sets of log n. So log square n total coordinates. So that would get me something like, if I just did that directly, you would get something like the expected value is greater than or equal to log n duv or something, right? And this thing is at most log square n duv. So if I just repeated log n times, this is what I would get if I just added them up. So first we're off by a log n factor. So maybe instead of pile them on, I can also kind of like average them. So I'll scale everything down by a log n factor. Okay. So we can scale down. And so at least now we're at the right scale. But I'm still have some issue of expectation, right? I'm trying to remove the expectation. I'm trying to get a high probability. Or maybe it's a little bit easier to see. So I'll put it back to where it was before with the extra log n. But obviously that's the same up to scaling. That's not a big deal. And suppose, again, scaling doesn't really matter. So suppose I said this was just 1, right? So let's just scale everything so that the distance is 1, figure out the idea, and then obviously it'll scale back up because everything's multiplicative. So in this event, How can I show that? So the expectation is very large, right? I'm just trying to get at least one. The expectation is like log n or something, or I could make it a bigger constant. It could be 10 log n. The expectation is much larger. How can I show that with high probability? Well, first, Markov's, I think, is usually about how much you go over the average. And here we're saying you shouldn't go under the average too much. The average is already log n, and we want to show it doesn't get under 1. Or something more direct. So we pointed out that each one of our coordinates is a contraction. So each coordinate's independent and it adds at most 1, or DUV if it wasn't rescaled. So you have these independent variables that contribute at most 1, and on average they're going to add up to at least log n. So now we're in that Chernoff regime, that high probability regime. The average is way larger than any individual contribution, so it becomes e to the minus, log n. Okay, so it turns out to be very useful that each coordinate was also a contraction. Because then that lets you get concentration. Okay. So that's just the idea. So we'll take the average of these embeddings, and then we can apply Chernoff to get the union bound over everything. Okay. So that's how you can take any metric and embed an L1 metric with this kind of sampling distance trick called Frechet embeddings. And next time we'll see what I hope is a compelling application uh, of this tool. Okay. All right, good. We did it. It worked. That's great. Streak starts at 1 again. Okay. All right, let's get started. All right, today's about sparsest cut. So last time, well, we've been doing dimensionality reduction. So last time we talked about L1 metric embeddings, right? So this is sort of an alternative to what we had done last week, which was these high dimensional Euclidean embeddings, going from high dimensional Euclidean space to log n dimension, basically for free. And today, or yesterday, or Monday, third time's the charm, uh, we talked about trying to embed things in the L1 metric, which is sort of natural for combinatorial settings. And what we showed was that you can take any metric this time, like any metric just given as a black box. As long as it satisfies the triangle inequality, you're going to get this constraint. Okay, so you're going to get you're going to be able to take your vertex and embed it into log square n dimensions, and the L1 distance is going to preserve the original distance up to a log n factor. Okay. So, and we'll see why that's useful today. The algorithm was very clever, I think much more subtle than, for example, the dimensionality reduction where we just hammered it with Gaussian random variables. We were doing this like sampling thing where to generate one coordinate, you'll sample a set of vertices or points, and then you measure the distance to every other point. And at some level, we discussed a little why that's has some intuition. It's always contracting. Um, and the proof was actually kind of subtle because you have to do this sort of telescoping series with these radii, which are chosen based on the number of vertices, points that are nearby, right? So it feels like it's kind of threading a needle. But nonetheless, it works. And yeah, that's what we did last time. And we also discussed how to sort of take this expected value and we had a sense that it was going to be amplifying or repeating to turn into a high probability result, but we also kind of teased out the details. Ultimately, because every coordinate is a contraction and they're independent, right? So then you're ultimately going to get the concentration because you're trying to get, within a log n factor of the desired distance, and every one of those independent quantities is at most a distance. So it's a log n, so you have the right thing for Chernoff. Okay, so today, well, we're really going to try to talk about sparsest cut, which is it's a really important problem, but really highlights the value of these metric embeddings. But first, I need to teach you a little bit about LP duality. I think some of you have, but how many of you have been taught LP duality in a class before? Yeah, maybe you've heard of it. How many were presented a proof? Okay. It's not that bad, but it's totally math, so sometimes I don't do it. Um, but what I will is just teach you what it is today and give you some examples. Uh, yeah. So okay. So the example I'm going to use is max flow min cut. So I've kind of preloaded some slides I typically use in algorithms class just to get us warmed up in case you haven't thought about flow in a while, right? So flow is a very natural question. You're given some kind of graph, and at a high level you want to know how well connected are S and T, right? And there's many different ways to ask this question. Uh, this question was apparently considered by Rand Corporation back in like the Cold War. So this is like a train network of Russia or something, and it's like, okay, if you wanted to like disrupt the connection between two major cities, what's the minimum number of spots you need to hit? Okay, um, so that's where a lot of operations research was coming from. Uh, But this question is also relevant, or extensions of this question in something like chip design, right? So you need to connect all these components. You want robust chips. So a lot of chip design, like the finest details, are actually automated. So they're the output of certain network design problems. Uh, People who study social networks at a high level. Uh, so S, that's us in Purdue, and T is I guess where my grandmother would be in Japan. And at some level, like how well connected are we in a social network? This is misleading because I don't think my grandmother knows how to use the internet. Um, okay. But the World Wide Web, right? So when Google makes a search engine, it does a lot of network analysis, and it'll ask questions like, okay, to some extent, how well connected S and T are is some proxy for maybe how similar they are in content. Okay, so there was a lot of, by now it's sort of old news, but this idea that you can actually extract information out of the structure of the World Wide Web, that was like a really big breakthrough, right? So anyway, you all know this. All right, so there's a bunch of different ways to ask this question. How well are S and T connected? One is there an S to T path? That's like depth first search. Another might be, how many different S to T paths are there? How many ways can I get from point A to point B? Okay. That could be a lot. You could look for like short hop paths. How many ways to get from S to T in like 3 hops or something like this? People do look at this. 2 hops I think is very popular. The length of the shortest S to T path. I'm just rattling off questions that you may have seen in your algorithms class, right? You might be in a model where if T is closer to S, they're more similar. How many shortest S to T paths? Classic homework problem. Here's an interesting question. If a random walk started from S, what is the expected number of steps until we reach T, which might be infinite, right? So the smaller it is, it kind of suggests that T is kind of more similar or closer to S. Finally, the question we'll discuss a little bit, how many edge disjoint S to T paths are there? Right? This is really the max flow question. And what is the minimum number of edges you need to delete so that S can no longer get to T? It's the min cut question. This is the Russian railroad question. So, right. So there's many questions one can ask. All right. So we'll focus on the maximum min cut questions. But let me frame it a little bit differently. Well, if you took it with me, then this is how you saw it. But if you didn't, maybe. So what is the maximum number of edge disjoint paths? Okay. So I kind of think of this as a packing problem, where you can take S to T paths. You can pick any S to T path that you want. And you want to take as many as possible so that they don't share any edge. Okay, so it's a packing problem. I'm kind of packing paths into edges. It's a funny packing problem because there's exponentially many paths you can take, but still, you're just trying to stuff things in. And yeah, I think yeah, okay. So that's an example of a packing problem. And the other question, sure. So I can think of an ST path. So the limited resource is edges. I can only use each edge once. And a path from S to T, I think of it as using up all those edges along the path. So I kind of think of like those edges as containers and sort of stuffing the path into the container. Yeah. But in general, you're trying to take as much as possible of something subject to size constraints. This is many size constraints, one constraint for every edge. It's like packing a suitcase. The other kind of dual problem, I'll explain what I mean by dual in a moment. What is the minimum number of edges you need to disconnect S to T? Okay. And I want to think of this as sort of the opposite of packing paths into edges. So saying that I disconnect T from S is like saying once I remove these edges, there's no path left, right? So I can think of that as saying that each edge will contain any path that goes through it. Okay, there's exponentially many paths from S to T. What's the minimum number of edges you need to take to cover all of the paths? Okay. So packing and covering problems are very natural. This is maybe sort of funny because it's exponentially many paths, but otherwise the structure is kind of very straightforward. So you're often in situations where you're trying to take a lot of something subject to size constraints, or you're trying to kind of cover all these constraints, but take as few as possible. It's a minimum cost kind of problem, minimum number of edges. Okay. So good. So these problems are what we call dual to each other, because I'm either packing paths into edges or the edges are covering paths. So, okay, this is something that actually is really, really useful. So, okay, well, this isn't the second example because it's not that class. Okay, so this direction is actually not so hard to see. We'll do it quickly together. But it says that the maximum number of disjoint ST paths, the most number of paths I can take, is at most the minimum number of edges in any S to T cut. Okay. And this is in fact going to be true of any packing covering situation like this. And maybe when we go through the proof of just this, you'll see, oh, okay, we're not using that much structure after all. But can anyone in one shot explain why this is true? And edges? But why not? Well, how come n minus 1 doesn't work? How come it's impossible to have n minus 1? Okay, because they're disjoint. So, right, so if we were to do it slowly, suppose I have some collection P, capital P, of edge disjoint paths, and I have some set C that's an S to T cut. Okay. Then, let's see what happens. Okay. So this should be less than equal. I accidentally erased it. Um, so I can write size of p as a sum of ones, one for each path. And I know that since it's a cut, okay, there's at least one edge from every path. I keep messing up. And I know the paths are disjoint. Okay, so taking that union and the sum is the same. I'm not double counting anything. And then finally, now we're just looking at parts of the cut and taking the union of them, and they're disjoint parts. Or no, it's already taken the union. So this is at most the size of C. Okay, but there's nothing really about paths and cuts in this. All that mattered is that the cut contains at least one edge from the path. Or yeah. Okay, so this will always come up. This kind of less than equal inequality where packing is less than equal to covering when the problems are dual to each other. The details might be slightly different, the notation might be different, but this is always the easy inequality. Okay, so the question is, are they equal? And assuming you satisfy the prerequisites for this class, you do know that they're equal. So, but I'm going to give a different proof. Okay, a randomized proof. Where you don't have to, I mean, when I give this lecture in algorithms class, Bellman-Ford is actually quite involved. It's like the most complicated, or maybe one of the most complicated algorithms we teach in that class. It's never clear that I present it very clearly. So I'm going to give a different proof that doesn't require an algorithm like Bellman-Ford. Okay? And maybe simpler. Although we will take something for granted. Okay, so there's some notation, but I think we've used this notation before, so it's not so surprising. So in the general setup, when you have dual packing and covering linear programs, okay, you might have a problem with the form maximize bx subject to ax less than equal to c. So I think b as like something good. I guess b for bounty, and maybe c can be thought of as capacities, and a is ax less than equal to c. That's limiting how much of x you can take. A doesn't have to be non-negative, but you can imagine a being non-negative. Okay. And then there's a dual covering problem. Okay. C for cost, I want to take y to minimize the cost. Subject to A transpose y being at least b, where b is a vector. Right? So this is matrix, so this is corresponding to many packing constraints you have to cover at once, so satisfy at once. And this is many covering constraints you have to satisfy at once. Okay. Yeah, that's a dot product. Yeah. So now the point I want to, or the thing I want to point out is notice that you have A on one side and A transpose on the other. Which if it's a 1-0 matrix, you can kind of think of, like, imagine, a 1-0 matrix between the rows and the columns. And then when you transpose it, you have the same incidences, but just the roles of row and column have changed. So it's just like the paths and the edges, right? The edges that hit the paths are exactly, the paths can fit into those edges. Like it's the same incidence structure. And here the objective has become the constraints here, which is also the only way to make the dimensions work when you're transposing. Okay, so you're flipping roles with C and B. Okay, and then in that particular configuration, we call them dual LPs. And now with dual LPs, we have this very strong theorem, okay, that says the value of these two LPs are always equal. And I won't prove it. We'll put it under the, we'll take it as a black box. But if you have LPs with this particular configuration, where A maps to A transpose, B maps to B, and so forth, then the values are always equal. And to show that the left-hand side is less than equal to the right-hand side wouldn't be that hard. It would be sort of analogous to what we just did. Only I would be kind of, instead of writing sums over edges and paths, I would be transposing A somewhere in the middle. Notationally, it might look different, but it's the same proof. The interesting part is showing that the packing is equal to the covering. Okay, this is extremely nice. For example, suppose you had a solution to the packing LP, right? And you wanted to know if it was an optimal solution. If you could solve the covering LP and get a solution with the same value, okay, now they're equal, right? Just like max flow less than equal to min cut, and they can certify each other. Um, and then, we'll have more examples. So, okay. So let's try to apply this to max flow min cut and give a slick proof. Okay. So I want to write max flow as a packing problem. So I want to write it as a path packing LP first. Okay. And so now I'm trying to take as many paths as possible. I can only assign non-negative values. You can't take -1 paths. But there's certain constraints, right? What are the constraints? The packing constraints, just to make sure we're on the same page. Uh, no, I mean, there could be edge capacities. I'm not sure. We'll find out if I included weights or not. But it's not too essential. So if I wanted to write a packing constraint, right, AX less than equal to B, what would A and B be? Or what are the first, just what are the rows? What are the constraints if this was an LP? Sorry? What's C? So you're trying to take as many paths as possible, subject to. Yeah, so in linear terms, that's saying, okay, the total amount of edge, the total amount of paths I take containing a particular edge should be at most the capacity of the edge. So I guess we do have capacities today. Yeah, okay. Uh, so the dual LP, so we're just working through an example of what this A transpose might look like. Okay. So remember, the C down here now becomes part of the objective. And the constraints down here become variables. Okay? Yeah, in a fractional way. So capacity doesn't have to be, no. Yeah. So this will actually get us max flow min cut altogether. Yeah. In fact, I don't think we're going to do edge disjoint paths. We'll actually do max flow is equal to min cut. So if max flow is naturally a fractional thing, um, yeah, we won't that, yeah, but we will do, okay, I'll get there. Um, but what would the covering constraints look like, right? So I'm trying to model like fractional ST cut. Yeah, so if you kind of transpose this incidence, right? So you're going to have for every, so there's variable for every ST path. So now you're going to have a row for every ST path. And if you transpose the incidence, then you're still going to be summing over the edges in the path. And the coefficients remain 1. So it's going to say that, so you're trying to take the minimum cost set of edges such that for any ST path, you're taking at least one edge total in a fractional sense, right? That's like saying you have to cut every path. Okay, so this is still kind of mechanical. This is just going through what A transpose is. It's our variable saying we're going to take the edge. So CE is like the cost. That's like the capacity. If it was an integer, yes. But we're doing a linear program. So this is a linear program I want to point out at this point. Okay. So, so B would just be the all ones vector then. Sorry? Oh, I don't know. Well, we don't need it for max flow. But okay. I mean, the packing LP in general is like you're trying to fill a suitcase or something, right? And then maybe the items are worth something. So you want to take the total largest value of items that fit in your suitcase. Yeah, it's quite natural. It's just that for max flow, you were just trying to route as much flow as possible, so it doesn't. Yeah, we treat the flows of equal value. Okay, so what we want to show today is that the max flow is equal to the minimum discrete cut. Actually, I've kind of departed from edge disjoint paths. I'm not worried about that. That will come from a different argument. So max flow is like the maximum fractional amount of paths you can fit. Okay. And I want to show it's equal to the minimum discrete cut. And the real emphasis is discrete. Okay. So, okay. Now, okay. So LP duality tells us that the max flow is equal to the minimum fractional cut. So that we actually get for free. Okay, so this is really just a property of like convexity or something ultimately. And so what remains is trying to show, well, okay, we also know that since the LP just relaxes the discrete problem, that the minimum fractional cut is at most the minimum discrete cut. Right? So what's left to show? Yeah, we just got to get this thing to be equal, or this squared and equal to that will give us that they're equal. Okay, good. So we can think of this as a rounding question, right? So suppose you have a minimum ST cut. And I don't know if that's minimum, but I think if you look at any path from S to T, the number should add up to at least 1. So I think it is a fractional ST cut. And the question is, how do you round in some extent, right? We have a fractional cut and I want to turn it into an integer cut. How do I round it into an ST cut? Any ideas? Yeah. Like independent rounding. Okay, so independent rounding. Um, okay, so okay, so independent rounding is a natural idea for every edge. You know, the one that's labeled 0.2. Let's flip it. Was probability 0.2. I'll take that edge, and hopefully I'll separate S and T. Right now, okay. Suppose I had S and T, and I just had like two edges, and they were both given value 0.5, which would be a. Oh no, that's not true. Let me put in one more. Okay, that's okay, right? So now if I independently round, what are the odds that I get an ST cut? It's not 100% at the very least, right? So I can easily sample all three, and I can certainly sample just two of three. So 1/2 chance here, and then I guess a 3/4 chance of getting at least one or something. Okay. So if I wanted to get that down to like almost certainly outputting an ST cut, I would need to scale up, right? And then at the very least, that's going to get me an ST cut of value greater than Y. So I'll just get O is less than equal to, I don't know, log N in the best case is what I can hope for. But so, so independent rounding, it just seems like it's a little error prone because I'm trying to get something very precise, right? I'm trying to round it from fractional to discrete with no loss. Yeah. Oh, okay. Can I do some deterministic? Yeah. And I guess maybe, I think, so the idea was, can I look at every path and take the biggest edge on that path? Which I think is equivalent to order the edges in decreasing order of value. And as long as there's a path from S to T using that edge, delete it. You got, yeah. So I guess, uh, I think it wouldn't be too hard to come up with a counterexample. Yeah. Okay, so for each, I have one path, and I treat the edges as a uniform as a distribution because they sum to at least one. So for each path, I can like try to cut it somewhere along the distance from 0 to 1. Okay, that's pretty good. My next worry though is that there's many paths. Yeah, sure. Oh, yeah. So this last suggestion of, oh, can I look at each path and look at is actually a good idea. And the only issue is that you have so many paths, right? Is there any way to kind of do something like that? You guys are actually really close to the idea. That's why I'm kind of egging you on. Something like this idea, but can get around this issue of many paths, because otherwise each of your paths is going to be cutting an edge, and that's going to be bad. Okay, how about this as a hint? What's the distance from S to T in this graph if we treat those as edge lengths? It's going to be at least one. Does that help? You can assume they're all short paths. The LP will be smart and not give you like much slack. There'll still be a lot of shortest paths. Okay. Okay. Well, we have to keep. Okay. Okay. Now what if I did this? So what if I embedded all the vertices on the real line from S to T based on distance from S? That may or may not be an accurate picture of the example, but you get the idea. That'll be step one. I'm using our edge lengths from the LP, and I'm computing shortest S to T paths. Now what? Speak. Okay. So we'll just choose a random value, uniformly random between 0 and 1. And, uh, some vertices will be on the S side and the others will be on the T side. And we'll take all the edges that are going across this cut. Okay. This is called a sweep cut. No, there could be like other edges and stuff, and there could be more vertices out here. I just drew a picture. Yeah, there could be more vertices out here. Maybe these edge lengths aren't tight, you know. Uh, it's possible that this edge here from point 0.5 to 1.0 could have length longer, but it's not affecting a shortest path. The LP will probably make them tight, but we won't rely on that. Okay. Okay, so then we output this. Okay. So, as noted, we could do an expectation argument, which is reasonable in a randomized algorithms class. Okay, so this is what I want to calculate. What's the natural first step? Sorry? Indicator variable, which alludes to linearity of expectation. So I'm just summing over all the edges, probability of the edge being cut. Okay, what's the probability of an edge being cut? Right? So I just want to fill this in. Why is it at most the length of the edge? Yeah, because it's being stretched out on the line, right? And it can't be stretched out more than YE. It's the shortest path thing. So this becomes YE. That's the weight of the minimum capacity of a fractional cut. So a random cut in expectation is going to be at most the fractional cut value, right? Okay, now how do I actually get an ST cut? So this random algorithm on an expectation is good. Now I want to guarantee that I get an ST cut. Basically, we want to de-randomize this. Yeah. Yeah, so, okay. If the average cut is good, then there exists a cut that's good. So one of these values of theta must be very good. So you can sweep through all the theta from 0 to 1. Okay. Okay, in fact, not only is this a random cut good, but it's like as good as possible, right? You can't do better than the minimum fractional cut. So what that actually tells you, you could do something at some levels. What does it tell you about all the thetas? So if I told you that the average score on the midterm was 100% and there was no extra credit, what is the worst score that anybody in the class got? 100%. So in fact, all the thetas will give you minimum ST cuts. Because the average theta is perfect. If there's any point that was imperfect. Okay, so that's maximum min cut. A randomized proof for maximum min cut, yeah. So it's going to be only the edges. We know that the length of an edge going forward is at most the length. Yeah. So the analysis doesn't get anything from edges that are not on the shortest paths. Okay, so this is very slick, and we have a little bit of time to talk about sparsest cut. Okay? But it's going to be building on these ideas, so it might go faster than you expect. So, okay, what's the high level idea? So, okay, so in the general version, you have a big undirected graph. I have a picture coming up, and for every two pair of vertices, you have some kind of demands. Say they're symmetric. Imagine you're like a telephone network, and it's telling you how much people talk to each other, which I don't know if people talk on the phone anymore, but they once did. And you want to, at some level, split the graph and delete relatively few edges and split up many pairs. So you want to disrupt the network. So it's like ST cut, but with many vertices, many pairs of STs, okay, of various different values. So this problem actually is probably much more commonly used in network design and stuff than ST cut. So Bell Labs needs to route many people and stuff like this. So, so in a simple case, maybe between every pair of vertices, I have demand 1. So it's just uniform. In that case, when I cut the graph with some set of vertices S, the total number of disrupted pairs is size of S times size of outside S. Okay, so that's what this ratio represents. What might be a good sparse cut in this graph? 3 edges in the middle. So this kind of cut, sparse cut, feels correlated with balanced cuts, especially with uniform demands, right? So this is actually used a lot for graph partitioning and divide and conquer problems, okay? And in fact, the graph partitioning algorithm is compute the sparsest cut. If it's not balanced, go into the side that's too big, compute another sparsest cut, and just keep going and nibbling away, and then you can get it to all collapse. So that's an exercise in the notes. I don't know if I'll put it for homework. It's not really randomized, but it's like, you know, a standard. This is something that people do a lot. It's very common to try to break up a graph into small parts. So, okay. So that's one common one, which is number of disrupted pairs. Size of S times the size of complement of S. There are other notions of sparsity. Some might put like the smaller of S and complement of S down on the bottom. But the bigger side is always at least N over 2, so it's kind of similar. Yeah. We'll do a different one later called conductance, which is based on something called volume, but that'll come later. So we want to do an LP approach for this problem in 5 minutes. So first, does anyone want to suggest how to write an LP for this? Sorry, I didn't do a great job of time management. So at some level, what I can think of is something like this. So imagine you cut a graph in half. That's sort of like, you can think of that as everyone on the same side having distance 0, and everyone going across the cut having distance 1. This is actually called a cut metric. You can take a bunch of cuts and, you know, sum up these ones and zeros and you'll get a metric. So in the numerator, it's saying, okay, let's come up with a metric, D, that at some level is not cutting too many edges. So I'm looking at the cost of each capacity of each edge and multiplying times the distance. In a discrete case, that's 1 if the edge is cut and 0 if it's not. Okay. And on the bottom, that's also like if I'm disrupting a pair, it should be 1 or 0. So what this is not an LP yet, but what this math program is trying to do is it's trying to spread out the vertices without stretching out very many edges. So the numerator is the edges being stretched out, weighted by their capacity or their cost. And the bottom is the pairs being spread out. You want to spread out the pairs, but you want to keep the edges short. Those are the demands. So in the uniform case, that's all ones, but I'm just presenting it slightly more general. Maybe I should have done all ones. It's too late now. And in the second idea, on the next slide, okay, maybe this is easier to guess. This is not a linear program because it's not linear, right? How can I make this a linear program? How can I flatten out this fraction? So it's good that it's just summations. That's like nice and linear. The only issue is that we're looking at ratio. Okay, I can basically normalize the denominator. The denominator has to be greater than or equal to 1, otherwise minimize the numerator. Okay, now you have an LP. You can just plug this into a box, and you're fine. I'm only going to briefly mention that the dual LP, so this is sort of like trying to separate many ST pairs, and the dual LP tries to route as much flow between all the pairs simultaneously. If we had more time, we'd do the dualities more slowly, but we'll focus on sparsest cut given our time constraints. So, okay, the question is, you can compute this metric, this sort of spreading metric. How do I round it into a sparse cut? And I think we're going to be okay. So, suppose I told you, as a warm-up, suppose I told you that the metric was on the line, right? That in general, the LP is just going to give us a generic, metric. But suppose I promised to you, for some reason, that DUV was really induced by a line embedding. The distance between it is a distance between the vertices on the line. How could I round this? Yeah, the same algorithm is actually going to work. We can pick theta uniformly at random. Now, you can do the calculations like we did before, and you can get, the expected cost is going to be very good, the expected number of edges cut, I mean, and the expected number of kind of demand that's separated is also good, but the exact same calculations as before. But, okay, so this is good. The LP opt is equal to these expected values, but we want the expected sparsity. I mean, they're not equal, right? You can't just put an expectation around the whole thing. So how do we deal with this? Basically, fractions are a deal pain in the butt. So slightly different trick, but similar in spirit. On the next page is I left all this white space thinking we'd have time to do it together. So if I set lambda to be the value of the optimum that I'm going for, and I can guess it with binary search, or actually the LP tells me lambda actually, right? Then I can say, this ratio is equal to lambda, and then just multiply it through. Okay? So we know that the expected value of this is less than equal to this on the right. And so there's some theta where this, the amount of edges you cut, is less than equal to lambda times the demand. It's that value of theta that now you can put back underneath. Okay, so this is just getting around this fraction of expectations. You just clear the denominator first, and then you can do your expectations. Okay, we're going to make it, I promise. Okay, we're actually very close. Now, we know how to deal with one line. Suppose I told you that the metric was induced by many lines, what we call an L1 metric. Okay, so the vertices are all embedded on several lines, and the distance between them is the sum of the line distances. What would you do now? No. What? Okay, so in this case, look, we can try the same denominator trick, right? So if I'm summing up this thing, I note that most lambda times this thing. That's just coming from the LP. And that also means in particular, right? If the sum of i's are good, right? That means at least one of these i's are good. Okay, so at least one of those lines is going to get you something very good, and then you can do the theta scanning on that. So, ultimately you do a sweep over all your lines. Okay, we're so close to finishing. I know you want to run out of here. Okay, so L1 metrics are good. All right, how are you going to round a general metric? It's no longer one of these nice ones. We're going to embed it in L1. So we're going to embed it in L1, and you can embed it into log square n lines and lose log n on the distance. Okay, so your value, your objective value will get worse by a log n factor. But ultimately, that log n distortion is going to give you a log n approximation, right? So this is supposed to highlight, okay, L1 metric is actually very nice. You can't do this with a Euclidean metric, right? So it's L1 that you can do it without loss. And the loss is just all the approximation factors just going from the LP, which gives you a metric, and turning it into an L1 metric. This paradigm is much more common than you think because cuts are often relaxed by metrics. There's a whole family of these network design problems. You're either routing flow or in the dual, you're computing some kind of optimal cut. And so this L1 metric thing solves like a ton of different problems. Okay, I'll leave it there. I went over, sorry. So thank you.